This lecture will address the legal aspects of GPS surveying. GPS is an acronym for Global Positioning Systems, which is a constellation of satellites put up by the U.S. Department of Defense. They orbit around 11,000 miles out in space, and this is an illustration provided by NOAA of what a navigation satellite looks like and how it's pointed at the Earth. So again, we'll talk about legalities, not technicalities. There are many courses, equipment manuals, and a lot of experience that can teach you the fine points of how to properly GPS survey. That's not what this is about. This is about the legalities of doing that. So, as professionals, surveyors must understand the basic principles behind GPS positioning and be able to explain it to a similar level to explaining how an EDM measures. The technology is similar. Notice this is the basic principles. That's because the actual physics and the calculations behind the process of positioning with GPS is very complex. It is literally rocket science, high precision rocket science. Surveyors are not expected to be high precision rocket scientists or geodesists. So geodesy is in one sense high precision rocket science, but it's the study of how satellites, which are not just man-made launched navigation satellites, but anything that orbits the Earth is a satellite. It's the study of how they move, the mathematical definitions of their orbits, their trajectories, and how they relate to the surface of the Earth. It is very precise. It's very different from anything in plain surveying. So for the basic surveyor to consider talking to the basic non-surveyor audience, client, adjacent owner, prospective employee, prospective client, attorney, jury, a basic fluency in the principles of GPS should suffice. And we will come back to the three most important points about the legal aspects of GPS surveying, in my opinion, which are to know the capabilities of the equipment, the limitations of the equipment, and how to identify faulty or suspect results. And similar to embracing the earlier advancements in surveying technology, surveyors should be able to calibrate and demonstrate repeatability with their surveying equipment. So we call it GPS. Technically, GPS is only the U.S. Department of Defense constellations, about 30 satellites, and they'll take some down, they'll put some up, but it's around 30. And technically, so GPS does not apply to satellites put up by other countries. We now call the greater envelope of available satellites Global Navigation Satellite Systems, or GNSS. That is the more common, or that is the more proper technical term for the entire constellation of satellites that are up there available by everybody that has put them out. In common society, we call all of this GPS, and we don't get hung up on the technicalities. But it's worth noting that besides the US 30 satellites, Russia has about 24 satellites up, known as GLONASS. The European Union put up about 30 satellites. Their constellation is known as Galileo. And China has put up about 30 satellites of their own. So they vary a little bit. They have a little bit different algorithms. The quality and the approach, the components will vary, but the technology is the same, and the latest generation surveying equipment can track and use all of them. So for the purpose of legalities and being able to explain it, let's just look in non-surveyor terms and as to how GPS works. So number one, GPS satellites broadcast a radio signal which provides their exact location, status, and the precise time that the transmission was emitted using onboard atomic clocks. Then, number 2, the GPS radio signal travels through space at the speed of light, which is a known constant. Third, a GPS device receives the radio signal, noting the exact time of the arrival, and uses these to calculate its distance from each satellite in view, or from the satellite that transmitted it. Here's where the magic starts. Once a GPS device knows its distance from at least 4 satellites, it can use geometry to determine its location on Earth in 3 dimensions. So let's look at how this breaks down. So if you know where one satellite is, and it's right here in the middle of this red sphere, and you have a receiver that can compute that. Now let's talk a minute about how that works. The transmission gives 3-dimensional geospatial coordinates, not latitude, longitude, not elevation, not northing and easting. It's like X, Y, and Z based on the Earth and its axis and the way that it's set up by geodesists. So that transmission says I was at these coordinates at this precise moment in time. It measures down to the nanosecond. The receiver receives that. It has a very precise clock, and it knows this many nanoseconds ago this satellite was over here. By knowing how many nanoseconds have transpired and this constant speed of light, the distance from that satellite to the receiver can be computed. So that's what this first image displays, is the satellite is here. Based on the time travel, you are this far away. It's a big old sphere, just a big old 3-dimensional circle. You could be anywhere on that sphere at that amount of time travel. Then with the second satellite, say it's over here. It's the green sphere. Well, imagine 2 spheres which overlap, not just circles, but 3-dimensional spheres. We're working strictly 3-dimensional here, which is totally different than basic 2-dimensional plane surveying. Now you have 2 intersecting spheres. So you have 2 intersecting 3-dimensional arcs that anywhere on those intersecting arcs, you are the correct distance from satellite number 1 in the red and satellite number 2 in the green. Add a third satellite. It's the blue one. The center of the blue one's right back here. Well, now if you can picture these spheres in space, but now you've gone from the 2 arcs where the first 2 satellites join to 2 points where those 2 arcs intersect the sphere of the third satellite, here and here. But you don't know which one of those is correct. It's an ambiguity. Add a 4th satellite. Right here next to the number 4 where the red circle is now is where the yellow sphere of the 4th satellite comes into play. And out of the 2 points that the first 3 satellites have it narrowed down to, only one of those is the correct distance from satellite number 4. We now have a position. This is how satellite technology works. Now, we could expound a whole lot, the reading material does, on the different nuances, procedures, the science behind how satellites are able to position on Earth. Here are a few things I want you to be sure to take away. 4 satellites on one frequency by math can produce a position on the Earth where you are. This is basically the simplest form of GPS positioning. This is what your smartphone does when it creates a position on your maps program or on an app that generates a latitude and longitude. It's creating a position using 4 satellites and distances from those. transmitted in one of the 3 frequencies that the current satellite platforms transmit on, which are L1, 2, and 5. 3 and 4 were reserved for or used strictly by the U.S. military. So L1 is the easiest to transmit. It's like AM radio. It picks up a long ways, you can hear it a long ways. It can also be subject to static, but it's the most reliable and the easiest to pick up. Notice there's no big 10-inch long GPS antenna hanging off of your smartphone. It's just got a little nub that receives the data just like from the satellites, just like it receives data from the tower. So it's not all that precise. You have satellites that are the size of a building flying through space at multiples of the speed of sound. The least little error in the clock creates meters of error. So under best conditions, the Department of Defense, or GPS.gov, says that this type solution, which is in your smartphone, which is in your automobile, is good for about 16 feet, or about 5 meters of a radius. So you could be 5 meters over there, it could be 5 meters over here. So it's kind of a 10-meter diameter circle of certainty as to where you are. That bears the question, how are we able to survey so precisely then? Okay, that's through basically 2 different ways, 2 different advantages that we have with current surveying equipment. One, imagine how much better the data of this one fix on the screen would be if, instead of just a single measurement from each of those 4 satellites, if you had 3 independent measurements from the same satellites at the same time. Okay, now you've gone from processing 4 solutions to processing 12 solutions, or 12 distances. That's what happens if these are multi-frequency satellite platforms and your receiver can read all 3 frequencies. That's 12 channels that it's transmitting. So you need, our new receivers can usually track 200 or 300 channels, so they can receive a lot of data. Now, with 30 satellites total in space, we can normally see 5, 6 to 8 maybe of those at one time. So you pick up a little bit there. But then by adding GLONASS, Galileo, and the Chinese satellites, now it's not uncommon to be able to see 30-something satellites in the field of view. That's 90-something or 100 different legs. So we get a lot more solutions to average for redundant measurements, for statistical analysis to see which ones are good and to mean out a good type position. L2 and L5 also produce better results because they are at higher frequencies and are governed by more stringent high precision navigation guidelines. So those are the first frequencies that you drop. You may not realize it if you're operating GPS equipment, but L5 is probably going to drop first. L2 is not far behind it, but it'll keep picking up that AM radio station known as L1. And that's an analogy, of course. And so, but with those L2 and L5s, the precision is a lot better. The computer programs will lock out, it will assign lesser weight or lower weight to the L1 frequencies and higher weights to L2 and L5 frequency solutions because it knows that it's more precise. So the greater abundance of satellites in all 3 frequencies, that's the main reason we've been able to progress in recent years. But even before that, even with single frequency, even with only tracking 5 satellites or 6 satellites at a time, just the bare minimum to get decent survey results, we had to occupy a point for hours to be able to get decent centimeter level precision. But the way we did that was differential GPSing. See, these different distortions and errors, maybe the atomic clock is off a little bit. Maybe the algorithm for the position that it transmits is off a little bit. Maybe there's some static coming through the ionosphere that messes with that signal. All of these things, about the best you're ever going to get, according to the Department of Defense, is about 1 meter. even with all the advantages that we have, your position could still be off 1 meter, but it's repeatable. It's repeatably, consistently off at that point in time by usually, my experience, anywhere from a little bit less than a foot to around 2 feet. That's important to know because that's what basically positional distortion. That's how much your position is actually off. Now that's still remarkably precise. That is black magic. But where surveyors are able to capitalize on this is knowing what that distortion is. That's going to be a 3-dimensional vector. And rather than call it distortion, now that we're thinking about surveying results, it's a correction factor. So it knows that tracking 30 satellites, 3 different frequencies, you're going to get a position that is 1.5 feet southwest and 2 feet higher than the actual true position. That same error, that same correction is going to be the same over a large space of Earth. Probably the entire state of Georgia, maybe in the whole southeastern U.S. is going to be subject to that same correction at the same time. So what high precision GPS does, it's called differential GPSing. Rather than focusing on what that initial computed 3-dimensional position is, by observing the same satellites at the same time, that correction factor becomes known. And instead of assuming coordinates, it measures the distances, the 3-dimensional vector between the base and the rover, or between 2 receivers, or between a network computed solution and where a network rover is. That correction data is where the black magic is in being able to survey to 1 or 2 hundredths of a foot under ideal conditions. Otherwise, it's just not possible. So that correction factor is determined and known and applied. Most simply in base rover, RTK surveying approaches, you determine or know or even assume the position of where the base is. And then those simultaneous transmissions give you the 3-dimensional vector from the base to the rover. It applies that to the known or established coordinates for the base. The rover's position is very precise. So that's basically how GPS surveying works. Understanding these things, we're going to go back to this. Remember this, the 3 main things that surveyors should be competent in and be able to speak to, besides the technicalities of their equipment and the software, and all of the 18 decimal place numbers that are associated with it. When dealing legally with the public, with the client, with the audiences that we've talked about, the surveyor should know, 1, the capabilities of the equipment. How good can it be? You know, what can it do? It can do this, but only in base rover. Or you can get results like this on the network. You can get results like this without a network or without a rover. You need to know just how good it is, which is basically the limitations. You should also know that even though the best that it can do is over here, if you're near a magnolia tree or under a bunch of dense pine or kudzu or next to a building or inside a building, it's not going to work. You might actually get a number because those radio frequencies may come through the canopy, may come through the glass, may come into the building good enough to get a repeatable position that it thinks is good. And that's why we pair up the phrase calibration and repeatability, because you can't repeat a position like that. Number 3, how to identify faulty or suspect results. You need to be able to analyze the data. You need to look at the standard deviations of the positions that are solved and understand when you've got bad data. So basically this is it. The reading material goes into greater depth, last touch, calibration, and repeatability. The positions can be calibrated by knowing what they are on HARN points, high accuracy reference network points, at the local airport or county GPS or GIS monuments. You can check the position versus your GPS by using calibration on known positions. Repeatability is what is really key, because you can get some of these errors embedded in your calculation. You can have multi-path distortion, which is not detectable without a redundant observation, without repeatability. It will give you a precise positioning while bouncing off of a nearby building, wet magnolia tree, rock bluff, or whatever, and it thinks that it's somewhere besides where it is. The only way to know for sure that you have not done that your position is repeatable, is with an independent, redundant observation. This might be from a different base point, more likely and more suggested, and the procedure that I use is to wait at least 90 minutes from that time of day, and not the next day, not the same time the next day, which would be 24 hours, but from that point in time, because the constellation of satellites and their trajectories only change a few minutes every day. So what you want to do is not be viewing those same satellites coming through the same tree canopy or through the same path in the sky to get your independent, repeatable, redundant position. You need to wait at least 90 minutes. More than that is great, but at least 90 minutes, because in 90 minutes time, most of the satellites that you're reviewing have cycled off to the west, and you have new satellites that have cycled in from the east, and you have a totally different constellation. Satellites are in totally different places, transmitting through different holes in the atmosphere. If you get the same result 90 minutes, 3 hours, 12 hours, 21 hours later, or different time, those differences in time in different days of the same week or so, now you've got something that you can go to court with. Now you've got something where you can say, this is a dependable, repeatable position. I have redundant calculations to back it up. In other words, if you can go back under different circumstances, at least 90 minutes later, and go to that same point and get the same positions, at least within acceptable tolerances, say 1 or 2 300ths of a foot, then that's all the repeatability that you need. But unless you do that, you don't have that. And I have personally, both in my professional practice and in talking with others, know of the software giving nice, beautiful results on a point that was as much as 3 feet away using the current technology. Before that, years ago, when L2 first came out and we were trying to do some RTK, you could get a good, statistically sound result that was as much as 6 or 8 feet from reality. And the only way we found that and realized what was going on is when we went back to try to set pins or try to verify that, or when something didn't look right in the office. So now that's probably more like a foot. You're probably getting into some of that actual error between the computed position from the satellites and where the differential position would be. But 7/10 of a foot to 2 feet is not acceptable. So that redundant observation is an absolute must. Many surveyors are not doing that. It's unfortunate, and they are putting out results that they will find to be unreliable, but only 1 to 5% of the time. I'd say now it's closer to 1% of the time. But you can get false results without a redundant confirmation. I'm saying right now about 1 or 2% of the time. That's 1% of the time too much. I'll close with this. A friend of mine asked, well, how do you know when that 2% of the time is? I said, when somebody else finds it and it's brought to your attention after you've already sealed and issued your work. That's not the time to find it. Do your own, do proper statistical analysis of your GPS positioning. Have a redundant observation. Add that confidence level. If you don't get it, make a third trip. If that's just not working, go to where there are good conditions, set intervisible pairs of points, get redundant observations on your intervisible pairs, and go back and shoot the point with an instrument. We've had to do that a lot of times over the last few years since we've embraced this new technology, but it's the only way to get a position that you can rely on. So these are some of the legalities and things that you need to know about for surveying with GPS equipment. Happy surveying.